Your tutorial presentation is now live.
Hello everyone, welcome to our tutorial on when not to trust your explanations. My name is Lakkaraju. Together with Shalmali, Joshi and Chirag Agarwal, I'm excited to bring this tutorial to you today. Before we get into the details of today's tutorial, let's quickly glance at the outline. We are going to begin this tutorial by providing a quick overview of some of the most popular explanation methods. We are then going to discuss about the technical limitations of these explanation methods. We are then going to get into the practical, ethical, and application-specific challenges associated with these methods. And lastly, we are going to conclude by discussing some possible directions for future work. Let's start with an overview of explanation methods. Before we get into that, let's take a quick look at the broad area of explainable AI. Explainable AI refers to this broad set of approaches that provide an interpretable description of the behavior of a given complex model to end users. And why do we really think this kind of an explanation or an interpretable description is needed? Let's try to understand that with an example. Now, let's consider the case where we have a complex model, which is potentially a Husky classifier. So it takes an image and classifies it as either being a Husky or not. In this case, we have actually input a Husky image and the model classifies it correctly as Husky with a very high accuracy. So far, everything seems great. We don't have any reason to doubt what the model is doing. It seems to be doing great, right? Now, if only we had access to some additional information, which is what features is the model exactly focusing on and what features it is using when making this prediction, we might be able to gain some additional insights. So let's try to understand that case as well. Let's say that apart from just getting the model label and its probability, we also have an explanation algorithm which tells us what features the model is focusing on when making this prediction, then what might happen. So in this case, let's say that we get this kind of a representation which indicates that the model is focusing on the snow in the image to make the prediction that the input image is a husky. Then it is clear to us that the model is not really using viable or valid features when making this prediction. The model is technically a snow detector and it is using spurious features in determining if an input image is a husky or not. Right? So having this additional insight into the model behavior has really helped us in determining, is the model making the predictions for the right kinds of reasons? And in this case, unfortunately, it turns out to not be the case, right? This is one of the many reasons why explanations can be invaluable when it comes to thinking about deploying machine learning models. Now, explanation methods have broadly been characterized into the following two categories: local explanations and global explanations. Local explanations typically explain individual predictions, the rationale behind individual predictions. They help unearth biases in the local neighborhood of a given instance or a data point. They help vet if individual predictions are being made for the right reasons. And the Husky example that we just saw basically corresponds to this kind of a local explanation. In contrast, there is another class of explanation methods called as global explanation methods, where the goal is to explain the complete behavior of a given complex black box model. Again, the point of these kinds of explanations is that they shed light on big picture biases which affect larger subgroups within the population. And they also help vet if a model at a high level is suitable for deployment. So we are going to touch upon some of the methods from both of these classes. So methods in these classes can actually be further split into several subclasses. Let's start with local explanations first. Local explanation methods can further be categorized into feature importance based explanation methods, saliency maps, prototypes or example based methods, and counterfactual based methods. Let me walk you through some of the most popular methods under each of these categories. I'll try and provide some quick intuition in each of these cases. Let's start with feature importances. As the name suggests, methods that basically output feature importances fall under this category, right? So the feature importances associated with a prediction are output by these kinds of methods. And a popular method in this category is called as LIME. I'm sure at least some of you might have already come across this name. So let's dive in to understand a little bit about what LIME exactly does. So, LIME at its core is basically a local explanation method which approximates a complex model locally by building a local linear model, which can be thought of as a simple explanation. And how is that done? Let us consider this particular point xi, which is denoted by this red cross in the picture. Now, the first step in LIME is that we sample points around this xi. As you can see on the picture, we have a bunch of these blue colored points that we have sampled around xi. We then use the black box model that we want to explain to predict labels for each of these sampled points. So now we have the labels in the image. We then weight these samples according to the distance to the original instance xi. So the points that are closer to xi get higher weights, right? So because they correspond to the local neighborhood of xi. And then we essentially learn a simple linear model on these weighted samples. So this simple linear model essentially serves as our explanation. If you can recall, a simple linear model like a linear regression or a logistic regression essentially outputs feature coefficients which can be thought of as feature importances. So the simple method basically allows us to obtain the feature importances that explain the local behavior of any given complex black box model. So this method is actually model agnostic. Now, under this category, there is another similar method called as SHAP, which actually leverages a game theoretic concept of Shapley values to output feature importances associated with individual predictions. While we are not going to get into the details of this method, SHAP is also often very well used in practice. Now, let's think about the next set of methods, which is saliency maps. So what exactly are these maps and how do we construct them? So again, let's consider the scenario where we have an input image which is being passed through this very complex model, and then the complex model is generating the prediction, which is the label associated this image. In this case, the complex model says this image is that of a junco bird. So the question that we want to ask here is what parts of the input are most relevant for the model's prediction, right? So which pieces of that image are the features or are the aspects that the model is focusing on when making this prediction? Right. And if someone were to magically give us this kind of an image where the pieces that the model is focusing on are highlighted in red prominently, that would be great, right? So such a representation is what is called as a saliency map. Okay, now how do we go about constructing such maps? How do we come up with an understanding of which pixels in the image are most relevant to the model predictions? Let's take some time to think about that. Okay, the first approach to computing such maps is called as a gradient, right? So a gradient is nothing but a derivative. The main idea here is that we are going to compute the gradient or the derivative of the prediction function with respect to each of the input pixels. And why do we do that? Because this intuitively captures the rate at which this prediction function changes for unit change in the input pixel, right? So that is pretty much what a derivative does, and we are essentially computing that derivative. Now, if we do that, here is how the saliency map that comes out of that looks like. As you can see, of course, it's highlighting some pieces of the head of the bird and the eye and so on, but there is also a lot of noise here, right? So simply computing gradient has problems like it being noisy, and this is exactly not very interpretable. So, prior research has come up with several methods to improve upon this very basic idea of computing the derivative or the gradient. So, the next best idea that was proposed in literature was this idea of smooth grad. And what exactly is smooth grad? Smooth grad basically means take your input image, replicate it n times, and add some Gaussian noise to each of these n replications, and then compute the gradients and average the gradients, right? If we do that, the image that you get is basically shown here. As you can see, this is somewhat more coherent and more interpretable than what we got by just using the vanilla gradient or the vanilla derivative. Right. And of course, there are several other methods which improve upon the quality of the saliency map, which are proposed as extensions of smoothgrad that, of course, we are not going to touch upon. But this is the basic intuition of how these kinds of saliency maps are generated. Now, the third kinds of approaches, which are also quite popular, are called prototype or example based approaches. And the idea here is very simple. The idea here is to use examples which could either be synthetic or natural to explain individual predictions. And I'm just going to give a high level overview of a couple of approaches here. The first one is this paper on influence functions proposed in ICML 2017. The high level idea there is to use this concept from statistics called influence functions to identify instances in the training set that are responsible for the prediction of a given test instance. And similarly, there is another approach called activation maximization, where the idea is to identify instances or examples, which could be synthetic or natural, that strongly activate a function or a neuron of interest. Okay, so that is the high level idea. So use some sort of examples, whether from the data or even synthetic examples, to explain individual predictions. That's the logic behind prototype and example based explanations. Lastly, we have yet another very popular area called as counterfactual based local explanations. Now, the idea here is to just think about this explanation as what features need to be changed and by how much to flip a model's prediction. For example, in this case, you see a couple of images and some areas highlighted, and what these pictures are trying to suggest is that what changes need to be made to the image on the left, which corresponds to the crusted auklet, to get the image that corresponds to a red face cormorant. And as you can see, the beak area is the main difference, and that area needs to be swapped to make a bird that belongs to one class to belong to another class, right? So why is this kind of an explanation even relevant? So this has some really good practical implications and applications. For example, let's consider this somewhat completely diverse scenario where we are thinking about loan applications, right? So an applicant has submitted a loan applicant to a bank, and the bank is using a predictive model to determine if this applicant should get a loan or not. Okay, so in this case, let's say that the predictive model being employed by the bank has rejected the loan of this particular applicant. Instead of just telling this applicant your loan is denied, it would be useful if we could actually provide him with some kind of a recourse, right? And that's exactly that can be done exactly by using counterfactual explanations. For example, the recourse could take the form of increase your salary by 50K and pay your credit card bills on time for next 3 months, and when you apply again next time, you'll get a loan. So that is a valid recourse, and such recourses can be output using counterfactual explanations. And the algorithms that generate these kinds of counterfactual explanations, we are just referring to them as the counterfactual generation algorithm. Let me give you some intuition about how these kinds of explanations can be generated. So, what you see here is a picture. You see a decision boundary of a complex predictive model, and the decision boundary is separating the feature space into two areas: the blue colored area, which corresponds to the positively labeled instances, and the skin colored area, which corresponds to the negatively labeled instances, right? So these are the two different areas. And let's look at the point X, which is currently negatively labeled by the predictive model. Right now, the goal is to find a counterfactual of X, which is actually positively labeled by the model. So, the high level intuition used by a lot of existing approaches in order to come up with counterfactuals for the point X is to basically slowly start nudging X in the direction of the decision boundary and stop once the nudged point crosses the decision boundary, right? So that is the very intuitive high level logic that is being employed, of course, in different forms and formulations, right? As you can see in this picture, X can be nudged to go to CF1, which is a counterfactual 1. X could also be nudged to go to CF2, which is a counterfactual 2. So both CF1 and CF2 are valid counterfactuals for X, right? And depending on the kind of algorithm you're using, you might either end up with CF1 or CF2. And there are different strategies for picking which counterfactual is the best. So most of the existing literature or the proposed approaches differ on how to choose among the candidate counterfactuals, and also how much access is needed to the underlying predictive models. For example, some approaches might prefer counterfactuals that are closer to the training instances because those are probably more likely to be valid instances. Others might propose counterfactuals which minimize the L2 distance or some other distance metric between the original instance and the counterfactual. So there are several different strategies that could be used to choose the candidate counterfactuals. Okay. All right. So now let's take a peek at the different kinds of global explanations. More specifically, we'll focus on three subcategories of global explanations. Just to refresh your memory, global explanations are those which explain the high-level complete behavior of a given complex, potentially black box model. So the first kind of approaches under this category are called collection of local explanations. Now, we have all looked at LIME approach in the beginning of this tutorial. So this approach basically uses LIME to construct global explanations. Let's see how. So LIME, as we know by now, explains a single prediction. That is, it explains the local behavior of a given complex model for a single instance or a data point, right? Now, you can't really examine all the explanations because our data sets could typically have tens of thousands or even millions of instances. So instead, the idea of this method called SP-LIME is to pick a subset of K explanations to show to the user. And how do we do that? So these K explanations should be picked in such a way that they're representative, that is, they should summarize the model's global behavior. And at the same time, they're also diverse, that is, they should not be redundant in their descriptions. What do I mean by that, right? So let's consider this scenario where on the right hand side, you see this picture with three dots. You have a black dot, red dot, and a blue dot. Let's say each of these correspond to different explanations or different linear models, right? Because LIME is fitting linear models. So now, once I have picked the explanation corresponding to the black dot, picking the explanation corresponding to the red dot is just redundant because they both are essentially corresponding to the same linear model, right? But once I've picked the explanation corresponding to black dot, picking the explanation corresponding to the blue dot is valuable because it is diverse. It represents a different hyperplane or a different linear model, right? So that is how we think about diversity. So this intuition is formalized using a submodular optimization problem, and a greedy approach is used to pick K explanations according to this method called as SP-LIME proposed in literature. So there's one way to think of a global explanation as a subset of local explanations. Now, The next category of global explanations is called as representation-based explanations. And what do we do here is the following. So let's consider that we have another complex model, which is essentially a zebra classifier. If you input an image, it will say if the image is a zebra or not, right? So in this case, we are inputting an image of a zebra. So it's rightly outputting the label as zebra with high confidence. Now, the question that we want to ask here is how important is the notion of stripes for this prediction, right? So there is this abstract notion that you and I as humans understand, but the machine does not really even know what stripes means, right? But if I were to ask these kinds of questions, like how important is stripes for this prediction, where stripes is just a concept I'm aware of, but the machine doesn't know. How do we go about solving this problem is the question addressed by representation-based explanation. Let me give a brief intuition of one of the approaches under this category called TCAF, that is testing with concept activation vector. What this method does is the following. Okay. So now, in order to represent this concept called as stripes, first this method suggests that we take a bunch of examples that capture different kinds of stripes. As you see here, the top row is full of examples of the concept stripes. Now, the bottom row is basically a set of some random examples which are not stripes. Okay, so these are two kinds of example that this method needs. And now all these are passed through to this model that we are trying to explain. So this is this complex model, which is a deep neural network, and we want to understand the effect of the stripes concept on the output of this model, right? So that's our goal. Now, all these different kinds of images, the stripe images as well as the non-stripe random images, are now passed through to this complex neural network. And what we see is we could take some of the intermediate representations, which will essentially be some vectors of some dimension, say m, and then this method proposes to construct this kind of a linear classifier that can separate the two categories of vectors, the vectors that correspond to the stripes examples versus those that correspond to the non-stripe random example, right? So construct such a linear classifier to separate these two classes of vectors. Now, the proposal or the solution here is that the vector that is orthogonal to this decision boundary, once we construct a linear classifier, we have this dotted line as the decision boundary, and a vector that is orthogonal to this decision boundary, here it is denoted by VCL, that denotes the concept stripes. Geometrically, the way to understand it is, so this vector is pointing towards the concept stripe and away from the non-stripe random concepts, right? So that's how we have to interpret this vector geometrically. So which means we have successfully represented this abstract notion of stripes now mathematically using this vector, right? Once we have such a representation, we can again play our derivative tricks. If we want to understand how important this concept is for the output of a particular complex model, what do? Take the derivative of the prediction function with respect to again this vector, and that will tell us what its importance is. So that's the rough idea behind this method called as TCAF. Now let's look at the last class of the global explanation methods called as model distillation based approaches. And these approaches are again relatively simple. The idea here is that let's say we have a black box model or any complex model, and then we have some data set of instances that we can pass through to the black box model, and then that will generate some model predictions, right? So we take all these as inputs and pass them through to the explainer or the explanation algorithm, which basically outputs a simple interpretable model that is optimized to mimic the model predictions, right? So you take this complex model and approximate it using a simple interpretable model, which is trained to mimic the predictions of that complex black box. That's a very simple idea, right? So take a complex black box, approximate using a simple model. And prior literature literature has actually done this using several classes of simple models. For example, there is work that basically approximates complex models using decision trees, which is often thought of as a simple interpretable class of models, right? As you can see, it's almost like a tree where the points are labeled according to what features are like splitting the tree and so on. So it's a simple intuitive structure. It can be thought of as a rule based model as well. Then there are other approaches that look at other rule based constructs as approximations to the complex black box models. For example, decision sets, which is basically a set of if then rules, a set of unordered if then rules, right? There has also been some work which basically takes a complex model and approximate it using another class of models called as generalized additive models, where the idea is to basically have a function corresponding to each feature that captures how the output varies as a function of each of the input features, right? So as you can see, different plots, each plot corresponds to one input feature. On the x-axis, you have the outcome or the predicted label. On the y-axis, you have each of the input features. So you see how the predicted label is changing as a function of each of the input features. With that, we have come to the end of this part of the tutorial. So we are concluding the piece about the overview of explanation methods.
So that was an overview of the different explanation methods that currently exist in the XAI community. Now I would like to talk about the technical limitations of explanation methods. Broadly, the limitations of current existing explanation algorithms can be categorized into four groups. First is faithfulness, where we talk about how some explanation methods do not actually reflect the underlying model. The second is stability, where we discuss about how slight changes in the input can cause large changes in the resulting explanations. Fragility talks about post hoc explanations that can be easily manipulated, and evaluation gap talks about the current non-existing evaluation benchmarks in the XAI community. Now we talk about faithfulness. The underlying question that we are trying to answer with respect to faithfulness is whether explanations change when the prediction of the model changes. So let us consider this image of a Junko bird as an example, which when feed-forwarded through a state-of-the-art black box ImageNet classifier gets correctly classified to its respective class with certain high confidence. An explanation algorithm generates some kind of attribution or heat map or saliency map that will inform an end user about pixels which the models think are in for or against the decision of the model. In general, the attribution map algorithm is a function of three parameters: x, that's your input; f, that is the model that we are trying to explain; and h is the set of hyperparameters that is associated with the explanation algorithm. For faithfulness, we are trying to answer the question whether explanations from two different models, that's f in the algorithm, have similar or dissimilar explanation. The notion of faithfulness is basically talking about whether an explanation is faithful to an underlying model. That entails to a setting where if we change some of the parameters of a model, then the explanation should reflect that change, right? So consider this the same example of the Junko bird, which when feed forwarded through a ImageNet classifier, let's say ResNet 50, gives some confidence scores. Now we take the same ResNet 50 architecture, but we reinitialize the weights at the top layer, let's say the logit layers, and that will result in a different confidence score, right? And in most cases, these two are not equal. The sanity check with respect to faithfulness is that this two models, F1, which is your ResNet 50, and F2, which is your ResNet 50 with the top layer reinitialized, should result in different explanation. As before, the explanation algorithm can be anyone, but the main point here is that we are making changes in the model F of the explanation algorithm. Now let us consider three explanation algorithms, that is a gradient input, guided backprop, and guided GradCam algorithms. The Science check paper from Julius Agarwal showed that if we start randomizing each layers of a classical inception V3 model, what we surprisingly observe is that these explanation algorithms result in similar explanation. This clearly rejects the notion of faithfulness, because as an end user I would expect that once these layers are randomized, the model behavior is not the same as the original inception V3 network, and so I should expect different explanation. But on the other side, all these explanation algorithms, as we see in the figure, uh, generates similar explanation, uh, thereby rejecting the notion of faithfulness. The sanity check paper also showed that other explanation algorithms like gradient and its different variants like smooth grad, integrated gradients, or input grad actually satisfy the property of faithfulness, where we actually observe substantial changes in the explanations on randomizing the parameters of the model. This concludes our discussion on faithfulness. We now discuss about the technical limitations with respect to stability. For stability, the inherent question that we are trying to ask is whether post hoc explanation methods are unstable with respect to small non-adversarial input perturbation. This question was first studied by Alvarez et al., and there has been some exciting work in this direction since then. So, with respect to stability, one way to quantify stability is by calculating the local Lipschitz constant for a given input x. Uh, This is similar to how we actually calculate the Lipschitz in the general criteria, where x is our input and f is our explanation algorithm in this case, which can be your favorite explanation algorithm like input grad or integrated gradients or smooth grad or line. So the question is, how much does the explanation changes for small points sampled around the neighborhood of x? For each given x, we now calculate the maximum Lipschitz constant value for a given explanation algorithm. We then average this Lipschitz constant value across the whole data set to come up with a stability score that resonates the stability of an explanation algorithm. Uh, if we look at the attribution map definition, then in contrast with faithfulness, which we're making changes in the model F parameter of the attribution map, for stability, we are making changes to the input X of the algorithm. So Alvarez et al. Showed that most state-of-the-art explanation algorithms are unstable, and they achieve high Lipschitz constant values across a given sample of 100 images for MNIST model. In particular, they showed that line is highly unstable as compared to other perturbation-based and gradient-based algorithms. Extending this result, Ye et al. In 2019 analytically derived bounds for different explanation algorithms with respect to their sensitivity measure. And eventually they proposed these stable variants of these algorithms. When we are talking about sensitivity or stability, we are basically saying that these stable versions of the algorithm will be achieving a lower Lipschitz constant values uh, as what was showed in Alvarez et al. We now discuss about a different notion of stability. Until now, we have been discussing about changes in the input x and model F parameters of an attribution map algorithm. Recent work has shown that most existing state-of-the-art explanation algorithms are also sensitive to the respective hyperparameters. This is an unwanted phenomenon because for an end user, I would want an explanation to be faithful to the underlying model and not to the hyperparameters which are chosen heuristically for each respective explanation algorithm. For instance, uh, surprisingly, it was shown that an expression algorithm like line can change its explanation drastically by just changing the random seed by which we are sampling the superpixels in the algorithm. Similar trends were shown for other explanation algorithms like sliding patch, where the explanation algorithm changed significantly with respect to the patch size of the algorithm. Uh, and for meaningful perturbation, it was the blurring radius. And for a smooth grad explanation algorithm, it was the number of samples that we are using for smoothing out the gradients. This concludes our discussion on stability. We now move on to the third technical limitations of explanation methods, fragility. Fragility talks about post hoc explanations that can be easily manipulated. Kinderman and Hooker et al.'s paper showed that explanation algorithms are susceptible to distribution shift in the input space. Again, here we are talking about perturbation in X parameter of the attribution map algorithm. The hypothesis behind this work was that the explanation shouldn't change with respect to factors that do not impact the model. By that, what I basically mean is that if I make some constant input vector shifts in my input space that does not change the prediction of my model, then I can expect that my explanations does not change too. Surprisingly, what we found out in this work is that even adding some simple patch-like effect or some heuristic kitty phase in my input images changes the explanation of my explanation algorithm. Moreover, in these cases, what we saw is that the same effect can be completely mimicked in the explanations too. In the previous work, we discussed about how explanations are susceptible to changes in the distribution shift of the input. Now we talk about how post-hoc explanation methods can be easily manipulated by adding some adversarial perturbation to the input space. Again, fragility talks about changes in input X of the parameters in the attribution map algorithm. So let us take this example from Dombrowski paper where we have given an image of a dog and our gradient-based explanation algorithm generates a saliency map as an explanation to an end user. So what Dombrowski showed is that we can obtain a similar image with a non-significant change to its input pixels, and that will result in a completely different explanation. It is to be noted that the prediction of the model for both these two original and manipulated image is exactly the same, but the perturbations are made in such a manner that both of these inputs give two completely different explanations. In particular, Gurbani et al. Proposed modification of the input with a small perturbation without changing the model prediction. Uh, if we look at the figure on the left, we'll see the original image and the perturbed image both are correctly classified to the same class llama, whereas the explanation for which is using a simple vanilla gradient in this case are completely different for the two images. The way Gurbani et al. Generates these images, perturbed images, is by solving the given optimization function. The task is to find a perturbed image which will result in an explanation that is uh, furthest from the original explanation, whereas the perturbation that we are doing on the input space is less than an epsilon, and also the prediction of the perturbed image and the original image is the same. The paper uses a L infinity norm in this case for solving the optimization function. One major takeaway from this work is that most explanation algorithms are susceptible to these kind of perturbation in the input space, and they result in a completely different explanation for these perturbed images. Thus, to the last technical limitation of explanation methods, evaluation gap. It is challenging to evaluate whether an explanation of a model behavior is reliable. There are two reasons for this argument. First, there is no ground truth for evaluating the explanation methods. If we already knew what was important to the model, we would not need to estimate the feature importance using these gradient or perturbation based algorithms. Moreover, it is also unclear which of the numerous explanation methods that estimate feature importance we should select, as again, there are no existing evaluation benchmarks. A fundamental question that we can ask with respect to an explanation algorithm is, are the explanations generated by these methods better than a random guess? Hooker et al. Presented ROR as an empirical measure for approximating the feature importance estimate in deep neural networks. The hypothesis is whether popular interpretability methods produce estimates of feature importance that are better or worse than a random guess. They also compared the feature importance with respect to a simple sober filter. The way ROR works is it removes the feature according to the importance generated by the explanation algorithms and then retrain several models using these different versions of the removed dataset. In the figure, what we see is in the second row, we removed 10% of the most important features as generated by smooth grad and the different variants of variation grad and random explanation map or a sober edge filter. And we do this for different percentages of feature importance. Surprisingly, what we found in this work is that most explanation algorithms are worse than a random guess explanation map, where the feature importance is distributed randomly throughout the image. So, when training these models, we can now generate testing accuracy, and which basically says that can my model detect the same images with just using 10% of the important features as compared to the whole image? And what ROR does is it then estimates average accuracy across all these different versions of the dataset, and that provides an estimate of the utility of an explanation algorithm. As discussed before, there does not exist a ground truth for evaluating attribution methods. BAM provides a carefully crafted dataset and models trained with known relative feature importance, and also proposes three complementary metrics to quantify the performance of these explanation methods by comparing feature attributions between different models and a different pair of inputs. So, how do they do that? BAM creates these data sets by exactly pinpointing to certain features that the model has to focus on to classify a particular scene or a particular object. So, for an example, if we take the object dog, what BAM does is it pastes this particular dog image across all the different scenes in the dataset, so that every time the model predicts the dog, it has to focus just on the dog, irrelevant of the background. On quantifying the performance of state-of-the-art explanation methods on these complementary false positive metrics, BAM found that certain methods are more likely to produce false positive explanations, that is, features that are incorrectly attributed as most important to a model prediction. This brings us to the end of the technical limitations. To provide a quick summary, uh, the lack of faithfulness or fidelity, Explanations are not guaranteed to be faithful to the model, and fidelity means that it is only guaranteed in the context of specific ecosystem of a model. With respect to stability, explanation methods are sensitive to both input perturbations and hyperparameters of the explanation methods. In terms of fragility, post hoc explanation methods can be easily manipulated, and it has been found that the explanations are also invariant to simple data distribution shifts. Finally, the lack of evaluation, we discussed about how the current XAI community lack formal benchmarking frameworks, and how we can also include some kind of human in the loop evaluation standards where end users can be used to evaluate these attribution methods rather than we relying on these heuristic proxy metrics for evaluation.
Hello everyone, thank you all for being here. I am Shalmali Joshi. I am a postdoctoral fellow at Harvard University at the Center for Research on Computation and Society. In this part of the tutorial, I will be covering some aspects of practical and ethical challenges that come about when deploying explanation methods in practice. After that, we will look at some application specific challenges, and that will allow us to have like some sort of an open discussion about what we should do from here in order to essentially engage more critically with explanation methods as they get more and more closer to applications and practice. Okay, so let's get started. We want to look at these challenges by trying to answer specific concrete questions. So the first one we want to see is whether explanations actually benefit decision makers in practice at all. And the entire motivation for the field of explanation is essentially to calibrate trust in machine learning models. As so we want to essentially see how close we are to getting to that goal. Um, and finally, we also want to see whether, as it's pertinent to this conference, whether explanations actually change perceptions of fairness of specific algorithmic designs, and whether we can actually mislead end users uh, actively into by obfuscating true model behavior adversarially. And if that is possible, then where do we go from here? Okay, so to first start with this important question of whether we are actually benefiting by using explanations in practice, particularly when it comes to decision making. It's useful to actually ground ourselves in specific applications and then see what insights we can generalize from here. So the first application that I want to highlight is one where a machine learning model and an explanation is used for treatment recommendations in major depressive disorder. For this specific mental health condition, the goal is usually to recommend treatments that will um, help the patient be more stable with respect to the treatment. So they shouldn't drop out of the treatment soon, and they should be stable in that they retain the treatment for at least some non-trivial period of time. Okay, and in this particular study, the authors want to answer two questions. One, whether having a machine learning model prediction that recommends treatments actually useful in improving patient outcomes, and second, whether different explanation methods how do they affect this accuracy specifically. Okay, so what they did was they created these patient vignettes, which essentially show some details about the patient, followed by a model prediction, which essentially recommends treatments ranked in order of their dropout risk. So if the dropout risk is low, they recommend the treatment highly, and then the goal is to see uh, how clinicians use this information and how it changes the accuracy of the treatment recommendations themselves. Okay, uh, since we also want to evaluate the use of explanations, they also will show specific explanation, which is feature-based explanation, which will essentially show what patient features are driving the model predictions in this case. Okay, so let's see what the authors found out. One thing is that when the recommendation given by the machine learning model, or this in this particular case, this vignette was accurate, the clinician's accuracy also remained unchanged. Okay, however, when the machine learning model, when the algorithm was providing incorrect machine learning recommendations for the treatment, then the accuracy of the clinician went down further. Okay, now, what happens when you put explanations into the mix, particularly feature-based explanations? So in this particular part of the study, they randomized over 4 arms, which is either provide no explanation or provide a placebo explanation, which essentially just suggests what the important saying that the recommendations are entirely based on patients' diagnosis, ICD-9 codes, which is essentially a set of administrative codes which are commonly used in machine learning healthcare models. Okay, and then clinicians were shown feature-based explanation, which is what you're seeing here, and finally heuristic-based explanation, which is essentially just relevant prescription heuristics based off of patient history. Okay, and then let's see now what happened with respect to the accuracy of what the clinician did based off of these explanations. And what they found was that accuracy still remained unchanged for correct recommendations when explanations were shown. However, for incorrect recommendations, the accuracy of clinicians went down even further. So this suggests that it's not necessarily conclusive that we are always benefiting from demonstrating, from giving explanations to clinicians, at least. Okay. So now the question is, when it comes to explicitly optimizing for trust, what is the effect of explanations in terms of calibrating user trust? So in this particular study, this is work from Hima, so he'll be able to talk in more detail about it in the discussion if you want, but I'm going to give a quick overview of what they did. The task here is recidivism prediction to figure out what is the likelihood that defendants will recidivate. Now, these the end users here in the study were law students, so somewhat of a domain expertise in terms of how such models might be used. The users have so there's an original rule-based model that is essentially extremely biased in that it actually makes recommendations entirely based off of other factors, but primarily based off of uh, race, and so it's definitely a biased classifier. And then the authors also came up with a surrogate model, which essentially behaves very closely to the original model, so it's sort of it's a surrogate explanation, but they essentially uh, made sure that certain sensitive attributes like racial information was not used in generating these explanations. And then, of course, the users were asked to rate which model they would trust more to be less biased, and domain experts essentially ended up picking the model or the explanation on the right hand side. What that suggests is even presence or absence of sensitive attribute was sufficient to drive trust in a specific AI model or even a specific explanation. And just by showing this particular explanation, one was able to manipulate trust in this biased model. Okay, so that is the extent of which we can actually miscalibrate trust using explanations to biased AI models. Now, what about notions of whether there's discrepancy with respect to fairness in decisions based off of explanations? In this particular study, the study was done on Mechanical Turk workers. It The way it proceeded was again, the task is that of recidivism prediction. However, they are not domain experts, but some information about defendants is shown, and then the likelihood of offending is shown, and along with that, 4 different kinds of explanations are shown. So I'll go briefly over what those explanations are. One is a sensitivity-based explanation, which is sort of a counterfactual, which essentially changes what the specific attributes of the defendant and then shows how the prediction might have changed. So of course, this explanation is specific to this particular defendant. In case-based explanation, they looked at like similar defendants to this target defendant, and then looked at what is the outcome according to the model on those cases. So it's a similarity based explanation, again specific to this individual. In input influence, they essentially interpreted coefficients, the logistic regression model that's giving this particular prediction. So you put pluses where having that particular feature increases the likelihood of reoffending according to the decision rule, based off of the coefficients that came out of that decision rule. And finally, note that this particular explanation is essentially going to be the same for all defendants. And finally, demographic explanations, which is essentially looking at subgroups that look like this patient based off of specific features, and then what the data reflects about outcomes for those specific defendants. Okay, so again, this explanation will remain the same across all defendants with similar feature values. Okay, so what actually happened when they got the responses? So there's some positivity that fairness perceptions do align with discrepancy in the model. Sensitivity and case-based explanations were more useful in have some increased sense are more useful in terms of attuning the perception of fairness, particularly sensitivity, where essentially if the model was being unfair in a particular decision, users were tended to rate it as more biased than any other explanation that they were shown. However, the sensitivity can actually be manipulated. Like all of these explanations could be manipulated to change that perception of discrepancy by just processing the data in a slightly different way. Okay. Now, finally, let's see whether you could actually just behave adversarially and end up misleading end users significantly by just fooling how these explanations were generated. And this is also work that has come out of collaborations with Hima, and this is the quick summary of how this process went. First, there was a completely biased classifier that was learned to predict whether or not somebody qualifies for credit. They also have other applications. I'm going to restrict to the credit application based off of their gender entirely. And so what you're seeing here is the feature importance rank of all the features that were used in the classifier to make that prediction. Of course, since it's entirely making its prediction based off of gender, gender ranks the first in terms of importance. And then what the authors did was create a new classifier E of X, such that for samples that are in the distribution of the data that was used for training, it behaves exactly like this bias classifier f of x. But if not, if the sample is out of domain, then it behaves like another classifier, which is a more unbiased classifier. Okay. And now, instead of showing explanations on F, the authors essentially looked at explanations on E, because clearly on all the training points that are in data, the model is going to behave exactly the same as f of x. So you could actually just create these explanations entirely based off of E for samples in F. And now you look at what is the most important set of features according to explanation methods LIME and SHAP, based off of this classifier E. And what they saw clearly was that because they had an unbiased classifier in the mix when generating E, the importance of gender in being like ranked the most important feature in predicting credit went down significantly with LIME and SHAP compared to other more benign features. Okay, so this is essentially how one could actually obfuscate classifier behavior by somehow manipulating these explanations, and this is one type of attack that has been shown in practice to be the case. Okay, so in summary, clearly we are at a point where there is a very mixed evidence of real world benefit. Explanations have been used to miscalibrate and manipulate trust and change perceptions of fairness of decision making models, and we can actually even adversarially attack explanations. So what do we do from here? Okay, now before going to what can be mitigated, we also want to look at methodological challenges when it comes to designing explanations. And so I'm going to continue to talk a little bit about ethical implications when it comes to specific explanation models. In this particular part, I'll focus on counterfactual explanations, although the overarching ethical questions are not necessarily common, specific to counterfactual explanations. It's more a general phenomenon. You can take a lot of existing explanation methods and contextualize the ethical challenges that come in. So let's see what that means here. I also strongly recommend looking at another critique of sharply value-based explanations from Elizabeth Kumar and Suresh, which talks about these issues for sharp values. Okay, so for counterfactual explanations, if you remember a quick review that we're going to give looks at how what specific attributes of a particular decision subject should be different so that some unfavorable outcome becomes a favorable outcome in a counterfactual explanation. So to ground it in a specific application, we'll look at a loan application model where a predictive model is f of x comes up with a prediction of whether for any given applicant their loan should be approved. If their loan is essentially denied, the counterfactual generation algorithm essentially looks at what the attributes of the applicant were and then figures out the smallest set of changes that the applicant could make to their own application so that eventually the predictive model will approve their loan. Okay, so this application is known as recourse. Of course, recourse can be as an application problem can be formulated in multiple ways, but here we look at counterfactual explanations as one way of generating recourses. Okay, so let's see what is happening under the hood mechanistically for a counterfactual explanation, and then let's see how value-laden assumptions get embedded as we design a counterfactual algorithm. So here we are operating with just two features, x1 and x2. So you're looking at this rectangle space. If your the decision boundary looks like this black solid line, where if you're on the yellow side, you're essentially going to be denied a loan and if you're on the blue side, you'll be approved of a loan. Now, if your features are X, and if you're denied a loan, which will happen based off of this decision boundary, then a counterfactual generation algorithm can provide potential paths in how you can overturn your decision by either taking the smallest set of steps using the red path to go across the decision boundary, or the green path to go across the decision boundary, and which one it gives or how many ever it gives is a design choice. Which one it gives is also based on the notion of cost of features, or the definition of what effort means in the counterfactual generation algorithm. So if x1 and x2 are equally costly to change, then we might look at a slightly different path than if x2 is harder to change than x1. Okay, and now let us see what problems can happen when we start to generate counterfactuals using this notion. Okay, so first and foremost, I want to mention that we do not necessarily assume that changes to X map to any concrete actions the user or the decision subject can actually take. Basically, the loan applicant will see that maybe if they increase their salary by $500, they will be approved of a loan, but that doesn't give them any kind of concrete steps on how they might actually be going about doing it. Should they change a job? Should they look for a promotion? Or should they do something else that will give them the extra $500 that they need to get this loan approved? Okay, so there is a mismatch in terms of mapping the explanation itself into concrete actions for the decision subject. I do want to emphasize that in this particular application, really the goal of all of these counterfactual explanations as applied here is to retain as much as a user autonomy as possible. So here you want to actually empower, in some sense, this decision subject to get the loan approved at some point. Okay. Now, the other challenge that can happen is, let's suppose you got step CF1 as a way to get your loan approved in 6 months. Within those 6 months, lots of things can happen. Maybe some laws changed. Maybe the bank went through an audit process of its own and updated the model, and now instead of the black decision boundary, the model looks like the red decision boundary. And now once you perfectly complied with the explanation, you came back after 6 months and you got here, but now the question is whether you still qualify for a loan. Now the discussion around this has been done deeply in the philosophical basis of algorithmic recourse. This is work from Suresh Venkata and Mark Alfano, where they try to discuss ethical grounding for the whole idea of recourse. Okay, so these are the challenges that we don't consider as design as modelers of explanations in terms of the implications on the end user. Now, something else can happen, which is changing X the way the explanation is recommended can change other external factors. For example, if you told the user to go get higher education, then they will take a hit on gaining job experience. Now, is that a compromise they want? Is that a compromise that's good for them overall? And does that actually retain their autonomy? Is a very important and critical problem. So there are certain things that the model is not privy to, which is essentially these latents that are external to the modeling choices that we've made, and our explanations can affect those in undesirable ways. They are not always beneficial to the end goal of the decision subject. It might affect some other objective that they're trying to optimize. So maybe that job experience is going to help them in a way that doesn't necessarily correlate with getting a loan in the next 6 months. Okay. And finally, the notion of cost or the burden for every user is quite different. If a person cannot actually leave their job, but can actually increase maybe their credit card payment by $50, uh, that might be easier for somebody than somebody who might actually be able to go to school, get a higher education, and get a loan approved that way by paying some extra money for childcare. Now, what is more beneficial to the user and what is less beneficial to the user is actually something that we implicitly put into the model when we put these functions in terms of costs or distances and so on and so forth. And those are quite non-trivial choices one has to make. Okay. So some of these have some partial technical fixes. So for example, if we think that it is very difficult to just show one explanation and expect uh, users to retain their autonomy, then one could provide multiple explanations. They can allow, a bank can actually allow the decision subject to clearly explore different counterfactuals within the constraints that they think they can comply with, or within the constraints of their life situations and so on and so forth. Or we can encourage using custom costs. Some world has already been explored by Hima and colleagues on that. One could incorporate more robustness in how the explanations themselves were generated by accounting for potential external shifts, like the data distribution might shift, something might change in the law. How can we preemptively account for those kinds of things without compromising too much on the quality of explanations for the person? And finally, one can be extremely transparent even about how the method, what the method itself was to generate these explanations, so that if there are obvious issues about how features were normalized and used for generating these explanations, becomes much more clearer to the end user. Okay, but there are still issues that are very, very difficult to fix, particularly, and the main lens to look at this from is the autonomy of the decision subject. So what does it mean for the decision maker themselves? First, we have to understand that it is in the decision maker's interest to preserve their proprietary black box, that is allowing them to make these awesome accurate predictions about whether a user will repay the loan. And so preserving that proprietary information is their goal, while also making sure that their customers are actually complying so that they get the best benefit of providing explanations, and also preventing any kind of strategic behavior from the perspective of the users. Okay, so if this is in the interest of decision maker, this actually is an extremely hard problem. If providing extremely accurate explanations is the goal, then the decision maker has to understand a lot about the life situation of the decision subject, which means increased surveillance and which means the need for causal knowledge. Because if the explanation don't directly map to specific causal steps that the decision user might take, the decision subject might take, we are actually not sure whether it actually improves any kind of real world outcome. Then again, as we discussed, design choices are very value laden. We make presumptions about mapping all features into one specific space with some costs associated with them. And that can create lots of issues in terms of like what we make assumptions about what the decision subject can actually do as decision makers. And finally, the main incentive, as we discussed, for a decision maker was to preserve the proprietariness of their essential black box, and providing multiple explanations can actually start to get murky, and it just would reveal the model. So then the decision maker loses incentives to actually provide explanations. Okay. Now, what happens from a decision subject's perspective? If the goal is to preserve their autonomy, then if they are trying, if they try to gain more and more autonomy, by getting more and more accurate explanations. It entails invasion of their privacy. And so this tension is very nicely summarized in this work by suggesting that in the best case, this reduces perfect explanations, everything reduces to a form of beneficent paternalism, where the decision maker has essentially figured out what is best for you as the decision subject and given you explanations based off of that. Maybe it means figuring out what is the best interest rate for you. Okay, and in the worst case, the decision maker can actually abuse explanations as a way to retain more power over you. And as we discussed, any kind of technical fix that we are looking at, we are essentially going at odds to decision makers' incentives. So we have a lot of challenges to grapple with. These kinds of discussions have also happened in a lot of other places. As I said, Elizabeth Kumar has discussed this in terms of SHAP values and how framing them as some sort of aggregate counterfact feature attributions actually is challenging. And doing any kind of the overarching theme that keeps coming is that doing anything meaningful in this space implies that your explanation should actually have some causal implication to the changes that we are expecting the user to make. And incorporating this kind of causal knowledge and explanation actually is at odds because it invades user privacy or is technically an extremely challenging problem where it's very hard to figure out what these kinds of causal relationships between people's attributes should be. Modeling choices that we are making are essentially value laden that we should be extremely aware of, even if we are not designing counterfactual explanations, but some other kinds of explanations. And in effect, they create some sort of a false perception of power and transparency where it might actually not exist. Okay. With that, I'm going to take a quick break and then we can come back and continue our discussion. Thank you. In this part of the tutorial, I'm going to cover some application-specific challenges of deploying explanation methods, and we'll look at some future goals that we can actually achieve to make explanations more robust in practice and the things we might want to consider while doing so. Okay, so to do that, I want to start with a clinical example again, where we might have a machine learning model that's deployed that predicts some sort of risk of adverse event like death of a patient and an explanation that goes along with it. And based off of those predictions and explanations, maybe the clinician comes up with a end of life care plan for the patient. So now let's think about what that implies in terms of in terms of explanations from the perspective of three specific stakeholders that might be involved in this whole process, which is the hospital, the clinician, and then the impact on the patient. So for a hospital that's deploying this kind of a model, if it is going to be used for determining patient interventions, then the standard of evidence of the benefit of the explanation is pretty high. And if a model got deployed without robust evaluation, from the perspective of the hospital, it would qualify as an irresponsible tool deployment. In this case, if somebody is creating policies for what makes sense for the model, then we might want to impose the same standards on explanations as we do on machine learning models as far as the evidence or standard of evidence is concerned. Okay, so now what happens from the perspective of clinician who's trying to use such an explanation? Particularly the clinician has some sort of an increased burden of moral commitment. They are first required to know whether they can actually correctly interpret these explanations and machine learning model predictions. If they think that they are not competent in interpreting these correctly, they are required to consult their peers or refrain from using explanations. In each case, they are then required to justify their decision of whether or not to use the explanation. If they did use the explanation, then how did they use it? Okay, so again, there's an increased burden on the clinician themselves. And then finally, let's look at the perspective of the patient, particularly from the point of view of specific ethical values that one is required to adhere to when providing clinical care. So, for example, we are essentially operating out of non-malfeasance in the clinical domain, which suggests that if explanations can be misleading and one can achieve similar patient benefit without using them, then we should not be using explanations to justify patient interventions. Okay? If we look at beneficence, then we are required to guarantee that using explanations will actually result in an overall positive outcome on the patient. Okay, if the explanations work well for certain subpopulations but not on others, then we are going to violate distributive justice within this domain. And finally, if explanations can be misleading and those interpretations can lead to harms in terms of whether or not the care plan goes a certain way, then we don't necessarily know that we are preserving patient autonomy. Okay. Another example that I want to bring up is the judicial domain. I'm definitely not an expert in this area, but if we are looking at proprietary black box models that are being used to make decisions of recidivism, and if we are currently in a situation where as a community we've decided that one specific notion of algorithmic fairness is not sufficient, which means that even if a particular proprietary black box guarantees that kind of fairness, we might have to have additional human intervention to make final decisions. And if we suggest that explanations are sufficient to go along with these procedures, but these explanations themselves that will these post hoc explanations can be misleading, then we are in a situation where we might actually want to prefer non-proprietary, extremely transparent and small interpretable models to actually operationalize notions of procedural fairness. And this was the main argument that was made by Cynthia Rudin and colleagues in this paper when they tried to start to figure out what actually is happening in the Compass black box designed by Northpoint. So this is one example I wanted to just highlight to make sure I cover different domains, but also to make sure this is one example where I feel like that debate comes head on with respect to interpretability, post hoc explainability, and algorithmic fairness, and what is more preferable versus not. Okay, so now considering all of these challenges, what should one do in terms of improving the design process or algorithms or even the way we evaluate, and how should policymakers and model designers think about explainability in general? So the first question we'll try to answer is whether we can improve explanation design processes. And some recent evidence has shown that yes, some iterative and co-design procedures can actually help in improving explanations. So if you remember the treatment recommendation system for major depressive disorders, where if you showed feature importance explanations, those were not found to be very useful for clinicians. However, when the authors discussed different explanation methods and eventually showed an explanation of dropout probability relative to the entire population, those kinds of things were much more actionable for the clinician, where they could then figure out if the relative risk of the patient to drop out is high, then they could actually engage with the patient a bit more to avoid that outcome. Okay, and they do have some other suggestions on what actually was helpful in the co-design process. Then are we even evaluating explanations the right way? And this is one study that showed that even in a simple task like where where we want to determine nutrients in a given picture of food, uh, depending on how you ask the question and how you design the task, determines exactly whether the evaluation of the particular explanations you are concerned with is helpful or not. So, for example, here users were shown a food plate and they were asked questions about whether about the fact that either the AI must decide whether 30% of more of the nutrients in this plate are fat, versus they are asked to decide for themselves whether 30% or more of the nutrients on this plate are fat. So it's a subtle distinction, but it's essentially um, a question of you're asking the user to figure out what the AI will decide versus what they will decide. And they were shown two different kinds of explanations. One is what we call an inductive explanation, which is more an example-based explanation, and the other was called a reductive explanation, which essentially was more about how the AI is understanding the image. So the AI essentially said, looked at the main nutrients from the plate and showed that and suggested that they know that these ingredients form more than 30% of the fat in this particular plate. So that's a deductive explanation. But here is what happened when evaluating on these the what is known as the proxy task, where they were told to figure out what the AI will decide, versus the target task, where they were told to figure out what they will decide. And they preferred different explanation methods in each task. And the interesting part is that when they preferred deductive explanations in the second task, they actually were able to recognize model errors better using the other explanation. But so the conclusion here is that subjective metrics like trust and preference don't necessarily reflect actual behavior of the humans in terms of the task uh, that is in question. So we do want to make sure that we design these evaluations very carefully as well. Okay, and so now I want to just quickly end with what we can actually do as model designers and decision makers or policy makers to engage with explanations a little more carefully. The first thing I want to say is that if you are a model designer, then we need to be transparent about what XAI can and cannot do. And then we do need to focus on specific application domains to design such explanations. Maybe it requires designing explanations for multiple stakeholders if autonomy is a big concern, like in the case of the clinical domain or the judicial domain, or even the credit application domain. uh, that we do have to be aware that when we are making such modeling choices, these are value laden choices, so we cannot separate out these issues when you are generating explanations. And we need to be aware of the ethical domain, the ethical values that are applicable in the specific application domain for which we are creating these explanations. And always focus on on evaluating benefits on real world outcomes. Okay. Now, if we are a policymaker and fiduciary, we do want to figure out what is the appropriate level of standard of evidence of showing explanations and whether it translates to some real world benefit. In a lot of cases, it should be done from the perspective of preserving autonomy, reducing over reliance on explanations, or using explanations to justify downstream behavior might be necessary in some cases, maybe not. And we should always audit explanations for equity and justice in terms of different subpopulations as well. Um, with that, I want to quickly conclude by saying that explainability as a technology is currently fragile, but we are making good progress in terms of figuring out real-world implications of using explanations in real-world in decision making, and the ethical implications are varied. They depend on the context, the method applied, or the application itself. And we've tried to provide some sort of prescriptive ways to engage critically with explainability. With that, I'm happy to take more questions, and thank you for listening.